It's filled with argon. You can see it's not kept particularly straight. You don't have to. That's a nice thing about optical fibers. One doesn't have to keep everything dead straight. Pulses are coming in from the left. And what I'm going to show you is a sequence of how this thing looks as you increase the energy of the pulses. So we're going to increase the energy up through the 1 microjoule range and up, and let's see what it looks by just looking at the side scatter. So here we have it. I hope it's reasonably visible. Yes, good. So this will repeat and repeat until I finish talking about it. You can see that on the right-hand end, on the output end of the fiber, initially it's dark and then it lights up, and you can see there's a bright bluish coloured streak or white, almost white streak that moves back towards the input face of the fiber as we increase the pulse energy. So it seems that whatever is generating the ultraviolet light, whatever mechanism is generating it, that mechanism is moving back up the fiber towards the launch end as you increase the pulse energy, which immediately suggests, yes, there's got to be some kind of focusing or something like that going on here. Some interesting nonlinear phenomenon is making this work. Well, you can then reach for your computer and a suitable modeler and put them together, get them to solve the nonlinear Schrödinger equation. And here is one of the results. John Travers generated this actually. So the pulse going in is initially 30 femtoseconds or so. We can see that, and putting in the correct dispersion from that model I showed you, you can see the pulses are compressing and compressing and compressing until they come down to just a few cycles in duration after maybe 7 or 8 centimeters. Very sharp spike, and at this point we see a kind of UV band marching off in a different direction on this distance time plot. It means its group velocity is different, of course, which is correct. So it's generated, it's very strong, and the remainder of the 800 nanometer light kind of does various interesting things, or not so interesting things. But what we're really interested in is that ultraviolet band that's generated. So what is actually going on here? So to try and understand what is actually happening, there are two things. There's the process of self-steepening, which is a well-known term in the nonlinear Schrödinger equation, and phase matching. Phase matching we can control with the dispersion by changing the pressure, as I showed you. And the self-steepening is very important too, because that provides the engine that enhances the generation of the ultraviolet light. So you need to have some kind of amplifier, some kind of engine driving it. You also need phase matching in order to generate light, of course, as we all know. But here we have both those things. So solving the nonlinear Schrödinger equation, including all the different terms, it actually agrees rather well with the experiments. The theory gives a little bit more, 1 or 2% more efficiency than we actually see in the experiment. But then with the theory, we can switch off the self-steepening term, or just remove it from the equation, and then the efficiency of generation of the ultraviolet is still there. We get, but the efficiency is about 1% instead of 10, so it's much, much lower. So the self-steepening term, of course, becomes very important when the pulse gets really very small, very short, a few cycles long. It's almost like a shock, rather than something that sings a little while and disappears. It's like a shock wave. So what we're seeing is that the fiber is allowing the pulse to become temporarily focused to a very short pulse, very nicely. Self-phase modulation in combination with weak anomalous dispersion does that for you. Then we have this self-steepening term becoming very important. We have phase matching to resonant radiation in the ultraviolet. The ultraviolet light gets generated, and once it's generated, it just continues to propagate in the fiber. This is nice. It's a very simple setup. There's no need for complicated optical items, whatever. It's just a short length of argon-filled fiber. Turns out it's very stable. It doesn't seem to suffer from optical damage. Of course, the gas won't suffer from optical damage. It's spatially coherent, so you can focus it down to a small spot. The ultraviolet bursts are ultra short. They're 10 femtoseconds or whatever. It's what the theory suggests. Threshold energy is very low, and the modeling suggests that we can even go down to 120 nanometer wavelength with this. There's just a list of possible applications. I'm not going to talk my way through them. There are people in the audience who understand these applications much better than me, but I think there are some quite interesting opportunities here. Okay, so let me now move on to my next topic. This is now a different nonlinear effect. This is Raman scattering in a molecular gas, and we've worked a lot with hydrogen. And I'm going to concentrate on a perfectly two-wave interaction in hydrogen gas, but in the backward direction, looking at backward Raman scattering. once again, here's a team. Alexander Nazarkin is the kind of the lead theoretician in this. Amir Abdelvand has almost finished his PhD, and he's been kind of running this work. So this is a very old slide that I've used many, many times, but it does illustrate what I want to say at the beginning, which is that with a photonic bandgap fiber, now I'm moving over to the genuine photonic bandgap guiding fiber, these fibers have a relatively narrow band of guidance. So this particular fiber has a 150 nanometer guidance band centered around 1064 nanometers, the Needham-Yag wavelength. This means that if you look at rotational Raman scattering in hydrogen gas, the first Stokes band sits very nicely inside that low loss window. The anti-Stokes band is also in there, but it's sort of a little closer to the edge of the band. Now this means that we have a built-in filtering which allows us to strongly suppress the normal vibrational Stokes band with 125 terahertz. Is much further outside. Normally that's the one you see. We can now focus on rotational and just basically ignore the vibrational because it gets hit on the head. Once its head comes up, it gets hit by the attenuation, so it doesn't have a chance to become stimulated. This means that we have a genuine two-wave interaction. We have the pump and the Stokes, ignoring the anti-Stokes for the moment. We have pump and Stokes waves and nothing else. So it's like a perfect toy system for playing with Raman scattering. I'm not going to talk my way through the equations, but I just want to illustrate that these four equations are all you need to model this system, because we know all about the fiber. We know its propagation constant. It's very well controlled. The light in the core. We know all these things. Furthermore, the filtering means that we only need two equations for the pump and the Stokes. And then, of course, we need the equations describing the quantum mechanics of the Raman transition in the hydrogen. And we can even, in some cases, achieve almost complete population inversion because of the very intense interaction in the core. I'm not going to talk about that particular case. I'm going to concentrate just on the case where the population inversion is fairly small. So we have three waves in a classical sense. We have a coherence wave, which is the molecules, molecular vibrational wave, a Stokes field, the optical field, and the pump field. These three waves interacting with each other. So just a little bit of fun here. This is a picture of some molecules. I've chosen a vibrational motion because I couldn't get the spinning to fit in very well in the picture, in the movie. So this is what happens in spontaneous Raman scattering. Some light comes in, a weak pump wave. It interacts with these molecules that are vibrating at the Raman frequency, and because there are many different coherence wavelengths in this randomly vibrating population of molecules, you could sometimes get generation of a Stokes wave forwards, or an anti-Stokes wave forwards, or a Stokes wave backwards, or an anti-Stokes wave backwards. You get all these different waves in the system. If you increase the power of the pump wave, then of course one can become stimulated. In this particular case, we're doing something additional. We're seeding the system with a weak backward signal. So we're taking an additional signal from another source at the Stokes frequency and seeding the system with that weak pulse or that weak wave in the backward direction. And this means that we can actually make the backward stimulated Raman process have a lower threshold than the forward. So we get a pure backward interaction. And now we have a beautiful system. Forward and backward waves coupled together by the Raman coherence wave. No other waves in the problem. It's very simple. The equations I showed you are valid for this system. And what happens in this case? Well, the forward wave and the backward wave, the optical waves, beat to produce a moving fringe pattern. That's obvious. The pitch of that pattern is around 500 nanometers. And this pattern drives the molecules. And it imposes some coherence on them. It makes their vibrations, sort of phases them up. Although this picture is a little misleading, of course we don't have total population inversion. Some of the molecules will not be excited, but if we excited them all, this is how it would look. No, we're not doing that. It looks nicer when you excite them all. So this fringe pattern is driving the molecular vibrations. The molecular vibrations, of course, are in turn causing more stronger coupling between the pump and the Stokes, and the whole thing is a virtuous circle, as you all know. I love this picture because it has so much physics in it. It has Bragg scattering, it has the Doppler shift, it has the Raman effect, and somehow they're all wonderfully mixed up with one another in this interaction. Okay, so that's the system we're looking at, and actually, for those of you who like funny comments, this is molecules doing a Mexican wave. Because I think some people have a problem with the possibility that matter can move very fast, although it doesn't move so fast here.